All right, welcome to Oceanography Basics Part 2. In this little section, we're going to talk about stability in the water column and changes in density with depth. In particular, we'll also talk about things connected to movements of water with regard to upwelling and downwelling. Okay, so we'll start with temperature. Here we can see the idea of thermo. This is having to do with temperature, and cline actually is like incline and decline. It's a area of rapid change. If we look at the diagram on the left, we can see that the highest temperatures are here at the surface, right? And it's relatively stable there. We don't see any change in temperature even as we drop down within the first 200 or 300 feet. Then we encounter this zone of very rapid change. This is the actual thermocline where temperature changes just drastically in a small amount of depth. And then finally below 1,000 feet, we have very little change in temperature and great changes in depth. If we look over here on the right-hand side of the page, you can see that in this section we have a warm surface layer in which the temperature is relatively stable and that area is mixed. Rapid change in the thermocline, and then relatively stable temperatures below that. Okay, so now we're going to tackle the halocline. Right? These are changes in salinity with depth. If we look at the graphic on the left, we can see the thermocline here. This is the same graphic we saw on the last slide. However, layered onto this is also the halocline. These are changes in salinity according to depth. You can see that the least saline waters are here at the surface. Makes sense in terms of our understanding of how salinity affects density. So more fresh water at the surface. Then as the salinity increases, we see this zone of rapid change in salinity from about 500 feet again down to towards 1,000, and then below that we get a much more stable water column with very little changes in density. So again, we have a zone of rapid change. This is the halocline here. If we look over on the right, we can see the same thing illustrated in this other style of graphic, right? At the surface, we have the least saline water, 32.5 parts per thousand, constant mixing of waves and currents. Then we have the halocline rapid change, 32.7 to 34.2 parts per thousand, and then greater than 34.2 parts per thousand at depths below that. Interestingly enough, we know that the coldest waters are most dense, and we know that the most saline or high salinity waters are also most dense. So we can see that those two things have their impact on ocean water when we measure density, and therefore greatest density of water is at the coldest, most saline places, which happens to be also at depth. Okay, now in this graphic what we can see is there's a little comparison going on here between how much of an influence temperature has on density and how much of an influence salinity has on density. I'll draw your attention over here to the left-hand part of the slide, and what we see here are packages of water. At the top we have warm, high salinity water. Beneath that, cooler, high salinity water, both of which make sense because warmer water is going to be less dense than cooler water. Since they're both high salinity, it's really the temperature that's going to be the influencer. But if we look down below, we can see here that here's cold, moderate salinity water. So these waters at the lower part of this column are less saline than the waters above. What this indicates then is that it's temperature that's doing the most influencing on the density of the water package. Then, just take a look here, we can see that the thermocline sits above the halocline, another indicator that temperature changes are going to be more influential than salinity changes here. Okay, so now we'll put this in a little geographic context. Here we have the equator. We've got the northern hemisphere and the southern hemisphere here. If we take a look at the color patterns in the graphic, we can see that at the equator the mixed layer is pretty shallow here, while at about 40 degrees north and 40 degrees south the mixed layer extends deeper. This is because of more significant weather, more wind and waves at those latitudes. We also can see that the pycnocline descends much further down into the water column at these same latitudes. It's also much shallower here at the equator. So the deep layer, which is stable and stratified, begins at a shallower depth here near the equator than it does in the more temperate areas. And the other thing to note is that this will vary seasonally, that this doesn't change, this doesn't stay stable throughout the year. Okay, let's take a look at the water column temperature throughout the year, as there's high amounts of seasonal variation. First, on this side of the slide, we see a temperature scale that will help us interpret the seasonal diagrams. The warmest temperatures are in red, the coolest temperatures are in blue. If we look at the winter, we can see that this water column is both very blue, meaning very cold, and also very uniform from top to bottom. Lots and lots of mixing of the upper layers of water in the wintertime, so therefore this turns out to be the least stable water column of all. Next, we look at the spring, and we can see that in the springtime we've got this lightning color at the top, much lighter green. Water column is beginning to warm at the surface, but it's still cool and stable down here. We shift ourselves to summer, and what we can see in the summer is that this water column begins to really stratify, and we see lots of darker red showing up at the surface and a much steeper drop in temperature as we look at the thermocline developing. Next, we want to notice that in this case, this is the most stable season in terms of the status of the water column. Finally, in the fall, as temperatures cool at the surface waters begin to cool down significantly. As those waters cool, they're more dense than the water below them, and they tend to fall down or sink down in the water column. When the water sinks down here in the water column, what it does is it forces other water back up, and we get a phenomenon called the fall turnover, where the surface waters go to the bottom and then the bottom waters come back up towards the surface. This is crucial in terms of circulation of gases like oxygen and CO2, as well as other nutrients that have settled to the bottom. What does that mean for the oceanic producers? If we see here, we've got all these planktonic producers here, all right, phytoplankton, and then all these macroalgae producers here. Both of them, one of the things that they have in common is that they need a lot of nitrogen and potassium and phosphorus. Those are things that are only going to come when waters from the nutrient-rich bottom get stirred up or somehow brought up to the surface. Okay, so here I'm going to give you a little bit of a challenge, right? What you need to do is you've got to try to make an explanation based on this graphic here about why you think both the plankton populations, that would be the spring diatom population, increases when it does. Why does it decrease? Notice that it just plummets down here in the summertime, all right? And you got to use the other information on the graph to help you interpret this. We've got phosphates and nitrates at the surface, we've got the amount of available sunlight, and this graph also measures the zooplankton population. So see if you can venture a guess as to why the phytoplankton or diatom population has such a spike in the late spring, early summer, then a plummeting drop, and then another spike in the fall. This graphic might help you a little bit. This is measuring nutrient inputs. A couple things we want to make note of, right? We've got this sunlight coming in from the out. Notice that it has photosynthesis and respiration here only at the surface. They are not shown down here, although respiration does occur down in the depths in the deeper ocean, right? And then we take a look at the idea that here we have this mixed layer here that stops, and we've got oxygen, which is going both out into the air here from the surface, and CO2 coming back into the water from mixing. Okay, so the last thing that we'll tackle here has to do with what happens when surface waters are moved by wind. Here we can see that we've got wind flowing along the coastal plain here, and then it veers and gets bent offshore. All right. When that happens, that wind comes along the surface of the ocean and pushes these waters out to sea. When these surface waters get pushed out to sea and move in this direction away from the shoreline, then other water from underneath has to well up and replace that water because this whole surface package is moving offshore, and this is where we get what's called upwelling. And this brings nutrient-rich water, right? Nutrients that have fallen down here after decomposition, they're now brought back up to the surface. So this slide then asks that question. If wind drives the surface waters offshore, right, in this direction, what happens? We get upwelling. If we get upwelling, we get nutrients brought to the surface, the phytoplankton bloom, and then in this graphic, the bloom of the phytoplankton is then reflected in the larger populations of other organisms as we move up the food pyramid or the trophic pyramid. So to summarize, what is upwelling? Upwelling is the actual movement of deeper waters up to the surface of the ocean, usually caused by either the flow of surface water out of an area, or it can also be caused by the sinking of cold packages of water from the surface to the bottom. Where does this occur, this upwelling pattern? This occurs in places like the equator, which we'll see in just a few minutes, but also occurs anywhere where there's an offshore wind blowing the surface waters away from the surface of the earth. Here you can see movement of the surface water. This drives nutrients that have sunk down into the bottom of the water column up towards the surface. All right, as those come up, we get phytoplankton blooms, and then zooplankton blooms, and then finally fish can really thrive on this increased nutrient rich ecosystem. Okay, so let's put this into a context in the hemispheres, right? So here we have an upwelling situation in this upper diagram. Wind is coming along the coast from the north, but because we're in the northern hemisphere, the winds get deflected to the right, and as a result, the water ends up in a net movement offshore. And when those offshore winds happen, when they're blowing out to sea, then these waters down below the surface flow up, bringing nutrients with them, and this is the classic coastal upwelling. Lots of nutrients, lots of really good conditions for organisms to live in the surface waters off the coast in an area where upwelling occurs. Next, if we look at the graphic below this, this is actually downwelling. Notice here that the prevailing winds are coming from the south. They get deflected to the right again. That blows surface waters onshore. The water piles up here and then sinks down, and this actually is the opposite. This is a downwelling pattern that brings needed oxygen and even in some cases CO2 down to organisms that live at depth. So the Coriolis force actually does influence whether we have upwelling or downwelling depending on the surface pattern of winds. Southerly winds here along this western coast, all right, coming from the north, and they're going to blow the waters offshore and you get upwelling. In the bottom graphic with the winds coming from the opposite place, from the south to the north, this will cause a downwelling pattern. Coastal areas aren't the only areas where this upwelling patterns can occur. If you look here and here, where we talked in our first section on oceanography about prevailing winds and about the winds near the equator, we have the tropical easterlies and the tropical easterlies in both hemispheres. They tend to blow towards one another. The result of these winds blowing towards one another as they move towards the equator, when they reach the area near the equator, they actually bounce off one another and then deflect away. And it causes the surface waters to deflect off the other water coming, the other trade winds coming from the other hemisphere. And as they do that, and they bounce away, moving the water away from the equator, this creates space here at the surface for deeper waters to flow up into on both sides of the equator. So we get equatorial upwelling from the trade winds bouncing into each other and flowing in opposite directions. So here are 4 takeaways for you. In the first, density is determined by salinity and temperature, with temperature being more influential. Second, generally speaking, the densest and most stable water is found deeper in the ocean, and the density and stability of the water column varies by season. The winter is the least stable water column, most uniform in density from top to bottom. The summer is the most stable water column with least uniformity, most stratification top to bottom. All right. Then lastly, upwelling and downwelling are crucial. They bring nutrients both up to the surface and down to depths, and they are integrally impacted by the Coriolis force and the prevailing winds in whatever part of the ocean you're in.